10 people are dead. The prototype is scattered across a hillside in Pierce County, Washington. Boeing's most radical gamble, the first pressurized airliner ever built, has just killed 5 of its own crews and 5 potential buyers from a Dutch airline. The program should be over, but TWA still wants the airplane. Pan Am still wants it. And Howard Hughes, watching from the sidelines with a checkbook and an ambition no one else would have entertained, wants one for himself. Not to carry passengers, but to live in. A private penthouse above the weather. This is how the most advanced airliner of 1939 became one man's flying apartment. In the summer of 1939, a Boeing rolled off the factory floor in Seattle that was not meant for any airline schedule. It carried the experimental registration NX19904, and it belonged to one man, Howard Hughes. The airplane was a Boeing Model 307 Stratoliner, the same type that TWA and Pan Am had ordered to carry 33 passengers across the continent in pressurized comfort. But Hughes didn't want 33 seats. He wanted fuel tanks, enough fuel to carry him around the world. The previous July, Hughes had circled the globe in 91 hours and 14 minutes, smashing the existing record in a modified Lockheed 14. That flight turned him into the most famous aviator in America. A ticker tape parade through Manhattan, front pages everywhere, a public that couldn't get enough of the lanky millionaire who treated records the way other men treated golf handicaps. And the moment it was over, he wanted a machine that could do it again. Not faster, necessarily, but in a kind of comfort that would make the achievement look effortless. He didn't want to arrive haggard and half-deaf after 4 days crammed into a vibrating cockpit designed for endurance, not livability. He wanted to arrive fresh, rested, fed, and looking like the flight had been easy. That meant he needed a machine bigger than anything he had flown before. The Lockheed 14 that had carried him around the world was a fine airplane, but it was a twin-engine medium airliner, cramped, loud, and about as comfortable over long distances as a park bench. The 307 was something else entirely. It was a 4-engine, long-range transport with the interior volume of a small bus and a cabin environment unlike anything else in the sky. It was the machine that could make Hughes's ambition look casual, and Boeing was willing to build him one, a unique variant, different from every other Stratoliner, tailored specifically to his mission. What made the Stratoliner worth hijacking for a personal mission wasn't its speed or its range. It was something no other airliner in the world could offer. The 307 was the first pressurized commercial transport to enter service. Every other airliner of its era forced passengers and crew to endure whatever the atmosphere threw at them. Turbulence at 10,000 feet, icing, headwinds that turned a 4-hour flight into 6. On rough days, airlines handed out paper bags and apologies. The 307 flew above all of it. At 20,000 feet, its cabin held conditions equivalent to roughly 8,000 feet. Think about what that means. The system erased 12,000 feet of altitude, 3/5 of the climb happening outside the windows, so passengers could sit in shirt-sleeve comfort while thunderstorms rolled harmlessly below them. 8,000 feet is about the elevation of Aspen, Colorado. You might notice a faint thinness in the air if you thought about it. Most passengers didn't think about it. That, in 1939, was not routine. It was radical. The idea that you could seal an aluminum tube, pump air into it, and let paying customers cruise 4 miles above the earth in something approaching normal comfort had never been proven in daily airline service. And the airplane that proved it could work was not some cramped experimental testbed. It was a genuine wide-body transport, 107 feet of wingspan, 74 feet nose to tail, with a gross weight of 42,000 pounds and a circular fuselage 11.5 feet across. That fuselage width deserves a comparison. Boeing's own 367-80, the prototype that launched the 707 and the jet age, had a cabin width of 132 inches. The 307's fuselage measured 138. Hughes's PISTON Penthouse sat inside a cabin 6 inches wider than the airplane that would define jet travel 2 decades later. A pre-war airliner, wider than the jet age's founding prototype. That is the kind of machine Hughes decided he wanted all to himself. Only 10 Stratoliners were ever built. One was the prototype, lost before it ever carried a fare-paying passenger. 5 went to TWA, 3 went to Pan Am. And the 10th, the one off SB307B, serial number unique, fuel capacity enlarged, owner singular, went to Howard Hughes. He had bought the most advanced airliner on Earth and turned it into a personal project. But the airplane Hughes acquired was not just luxurious, it was one of the most technically daring machines Boeing had ever attempted to build. And the story of how it came to exist begins not in a boardroom or a wind tunnel, but in the thin, freezing air above 30,000 feet, in the cockpit of a research airplane most people have never heard of. To understand why Boeing gambled on pressurization, you have to understand what flying felt like in the mid-1930s, and specifically, what it felt like for the passengers who were paying for the privilege. Airline travel in that era was loud, rough, and physiologically punishing. Cabins were unpressurized. Altitudes were limited to what the human body could tolerate without supplemental oxygen, generally below 12,000 feet and often well below that. At those altitudes, the airplane flew through weather, not over it. Turbulence was routine and sometimes violent. Air sickness was so common that it was simply part of the experience. Passengers who could afford to fly cross-country did so knowing they might spend hours being shaken, frozen, deafened, and nauseated. The airlines competed on speed and schedule, not on comfort, because comfort at 10,000 feet was largely a fantasy. One man had spent years proving there was a better option. DW's Tommy Tomlinson, a TWA pilot and engineer with a research streak that bordered on obsession, had been flying high-altitude test missions through the early and mid-1930s in a modified Northrop Gamma. Tomlinson took that single-engine airplane above 30,000 feet, altitudes where no airliner operated, and where the air was so thin he needed a pressure suit to survive. What he found up there changed the argument for pressurization from theoretical to urgent. Above the weather, the air was smooth, predictably, consistently smooth. The turbulence that made low-altitude flying miserable simply did not exist at 20,000 feet and above. And Tomlinson discovered something else: powerful, consistent high-altitude winds that flowed in rivers across the upper atmosphere. What we now call the jet stream, Tomlinson was measuring and mapping years before the term entered common use. An airliner that could cruise at 20,000 feet would not only give passengers a ride free of turbulence, it would be faster on favorable routes, more fuel efficient when riding those upper winds, and far more schedule reliable than anything fighting through weather systems at 10,000. Tomlinson brought the data back to TWA. He didn't just bring numbers, he brought a vision of what commercial aviation could become if you gave it enough altitude. The weather that canceled flights, injured passengers, and made airline schedules unreliable was not a permanent condition. It was a low-altitude problem. Solve the altitude limitation, and you solved most of the operational headaches that kept airlines from being taken seriously as transportation. TWA's president, Jack Fry, saw the future in Tomlinson's findings immediately. Fry was an aviator himself, a pilot who had worked his way up through the airline's operations and understood the difference between an airplane that fought weather and one that avoided it. He wanted an over-weather airliner, not a bigger version of the DC-3, not a faster version of what already existed, but something that operated in a fundamentally different part of the atmosphere. The question was, who could build one? Douglas had been working on the DC-4E, a massive four-engine transport that both TWA and Pan Am had helped finance. The DC-4E was supposed to be the next step in American air transport, bigger, longer-ranged, and more capable than the DC-3 that was already dominating domestic routes. But the program was going sideways. The airplane was overweight, over budget, mechanically complex in ways that alarmed the maintenance crews who would have to keep it flying, and, most critically from Fry's perspective, unpressurized. It solved the capacity problem without solving the altitude problem. A bigger airplane that still flew at 10,000 feet was a bigger airplane that still flew through thunderstorms. Both airlines were losing faith in it, and their money was drying up. Boeing saw the opening and moved decisively. Claire Egtvet, Boeing's chairman, recognized that his company held a card Douglas could not match: a proven four-engine bomber airframe. The B-17 Flying Fortress was already flying with tested wings, tested tail surfaces, and tested engines. Hardware that had been through military evaluation, stress testing, and the kind of abuse that frontline combat would eventually demand. If Boeing could design a pressurized passenger fuselage and mount it on that proven structure, they could offer TWA and Pan Am, something no other manufacturer could deliver. An airliner that flew above the weather, built on components the military had already validated in flight. The risk was concentrated in the fuselage. Everything else was borrowed. In December 1935, Egtvet put an engineer named Wellwood Beale in charge of the project that would become the Model 307. Beale was not starting from scratch in every sense. He had the B-17's wings, horizontal and vertical duct stabilizers, and engine nacelles as a foundation. But the fuselage was an entirely new problem. A pressurized cabin meant containing internal air pressure at altitude, holding a significant pressure differential between the inside and outside of the airplane for hours at a time, flight after flight without failure. A rectangular or flat-sided fuselage, standard in the 1930s, could not do it. Pressure loads concentrate at corners and flat panels. Over time, those stress concentrations crack metal, pop rivets, and open seams. The only shape that distributes pressure loads evenly is a circle. That single engineering truth dictated the most distinctive feature of the 307, its perfectly circular cross-section. Every window had to be small and rounded. Every door had to seal against pressure. Every structural joint had to handle loads that no previous airliner fuselage had faced. The 307 was not a B-17 with seats bolted in. It was a fundamentally new kind of aircraft, a pressure vessel with wings, and the wings happened to come from a bomber. Think about what Beale's team was asking passengers to trust: a sealed metal tube at 20,000 feet, where a sudden loss of cabin pressure would leave everyone aboard gasping in air too thin to sustain consciousness for more than a few minutes. The margins were real. The consequences of failure were fatal. The engineering had to be right. Not approximately right. Right. They had the concept, they had the structure, now they had to make a bomber breathe for passengers. And nobody had ever done it. The pressurization system that Beale's team developed for the 307 started with the engines. The four Wright GR182 OG102 Cyclone radials were proven military hardware, air-cooled, 9 cylinders each arranged in a single radial row, each engine displacing roughly 1,823 cubic inches. In normal cruise, they delivered 900 horsepower per engine. At takeoff power, that figure climbed to 1,100. Four of them gave the 307 a combined output of 3,600 horsepower in cruise, roughly the power of 7 modern sports cars, distributed across 4 nacelles on a wing borrowed from the B-17. Those engines already carried engine-driven superchargers. Centrifugal compressors geared to the engine's crankshaft that spun at tremendous speed to compress the thinning outside air and deliver it to the carburetors at something close to sea level density. Without the superchargers, the engines would have lost power steadily as the airplane climbed, starved of the oxygen they needed to burn fuel. With them, the Wright Cyclones could maintain rated power well above the altitudes where naturally aspirated engines would have been gasping. Boeing's insight was elegant in its simplicity: bleed a portion of that already compressed air off the supercharger system and route it into the cabin. The engines were doing the thermodynamic work of compressing air anyway. The 307 simply borrowed some of it for the humans sitting behind the firewall. But compressed air is not a pressurization system. It's a raw input. What you need is regulation, precise control over how much pressure builds inside the cabin, how quickly that pressure changes during climb and descent, and what happens if something leaks or fails. That problem fell to a Boeing engineer named Nate Price. Price designed an automatic cabin pressure regulator that managed the differential between the cabin interior and the atmosphere outside. The logic was straightforward, but the execution was exacting. As the 307 climbed through 8,000 feet, Price's regulator began closing the outflow valves, trapping pressurized air inside the fuselage. The cabin altitude would stabilize at roughly 8,000 feet equivalent and hold there as the airplane continued climbing. At a cruise altitude of 20,000 feet, a passenger's body experienced conditions identical to standing on a mountain in Colorado. Comfortable, breathable, unremarkable. The system could not maintain sea level pressure at 20,000 feet. Doing so would have required a pressure differential so large that the fuselage would have needed the wall thickness and the weight of a submarine hull. Price's compromise was the right one. Accept a cabin altitude of 8,000 feet, keep the structural loads manageable, and make the whole system light enough that the airplane could still fly efficiently. Testing the system was an exercise in ingenuity constrained by a budget that didn't anticipate building the world's first pressurized airliner cabin. Jim Cooper, one of the engineers on the pressurization development team, helped construct an altitude simulation rig from surplus oil drums. A sealed chamber where the team could pump air in, raise the internal pressure, and simulate what the cabin would experience at various altitudes. It was crude by any modern standard. It worked. Leak detection was even more elemental. Engineers pressurized sections of the actual fuselage and walked the seams with soapy water, watching for bubbles. Where a bubble appeared, a leak existed, a place where pressurized cabin air would slowly bleed into the atmosphere during flight, forcing the system to work harder and potentially failing to maintain the target cabin altitude. Every rivet line, every window seal, every door gasket, every penetration for wiring or control cables had to be checked individually. A single missed leak could mean the difference between a cabin that held 8,000 feet and one that crept toward 12,000. The difference between comfort and headaches, between safety margins and supplemental oxygen. It was painstaking, physical, hands-on work, the kind of problem-solving that required patience and good eyes more than advanced theory. And every leak they found had to be fixed, retested, and verified before the next section could be checked. The Mayo Clinic contributed physiological research on the effects of oxygen deprivation at various cabin altitudes, giving Beal's team hard medical data to design against. The researchers had studied what happens to the human body at 8,000 feet, at 10,000, at 12, at 15. They knew where the line sat between tolerable and dangerous, and they knew how quickly a person's judgment deteriorated on the wrong side of that line. Their input shaped not just the target cabin altitude, but the safety margins. How much headroom the system needed to maintain, and how quickly the crew had to respond if cabin pressure started dropping unexpectedly. The 307's environmental system was not just about air pressure. The cabin needed heating. At 20,000 feet, the outside air temperature could drop to 40 below zero. It needed ventilation. Stale pressurized air would become intolerable within minutes in a sealed tube carrying 33 passengers. And it needed humidity management because pressurized air drawn from superchargers is desert dry. All of this demanded a third crew member, and not just any warm body in a jump seat. In an era when most airliners flew with a pilot and co-pilot and nothing else, the 307 required a flight engineer, a dedicated system specialist seated at a dedicated panel behind the cockpit. The flight engineer's responsibilities were staggering in scope. He managed the 4 engines' power settings, monitored exhaust gas temperatures, adjusted fuel mixture and propeller speeds for each phase of flight. He controlled the supercharger stages that fed both the engines and the cabin pressurization system. He watched cabin altitude and differential pressure gauges, adjusting bleed airflow to maintain the target environment. If a window seal began to leak at altitude, the flight engineer would see the cabin altitude creeping upward on his instruments before anyone in the passenger compartment felt the change. He was the first line of defense against every failure mode that pressurization introduced. The flight engineer did not fly the airplane. He kept the airplane livable. And if something went wrong, a runaway pressurization valve, an engine failure that took one of the 4 supercharger sources offline, the flight engineer was the person who had to diagnose the problem, reconfigure the system, and keep 33 passengers breathing while the pilots dealt with whatever was happening outside the windscreen. It was one of the most demanding crew positions in commercial aviation, created from scratch because the 307 demanded skills that no previous airliner had required. On December 31st, 1938, New Year's Eve, the prototype Stratoliner, registration NX19901, lifted off from Boeing Field for the first time. At the controls was Eddie Allen, Boeing's chief of flight test, and the man the company trusted with every high-stakes maiden voyage. Allen was meticulous, methodical, and universally respected among test pilots, not for bravado, but for his ability to assess an airplane's character in a single sortie and communicate what he'd felt in precise, engineering-useful terms. He brought the 307 back down and delivered a verdict that cut straight to the core of what Price and Cooper and Beale had spent 3 years building. The great thing about pressurizing an airplane, Allen said, was that you shouldn't even know you're up there. That was the entire design philosophy in a single sentence. Not spectacle. Invisibility. The system succeeded when passengers forgot it existed, when the miracle of breathing comfortably at 20,000 feet was so seamless that it felt like nothing at all. The 4 Wright Cyclones gave the 307 a top speed of 246 miles per hour and an empty weight of just over 30,000 pounds. Those were respectable numbers, though not record-setting. But the real performance metric was the one no speed figure could capture. The 307 could cruise comfortably at altitudes where every other airliner of its generation was either struggling for air or simply unable to go. Speed was secondary to a transformative operational fact. This airplane lived in a different part of the sky. You're sitting in a Stratoliner at 20,000 feet. Outside the small, rounded windows, the temperature is well below zero. The air pressure at that altitude would leave you unconscious in under 3 minutes. But inside, the cabin is warm. The air is breathable. The ride is smooth because the turbulence and the weather are 4 miles below you, doing their worst to someone else. That experience, in the final days of 1938, existed in exactly one airplane on Earth. Then, less than 3 months later, the airplane came apart in the sky. So if you're learning something today, subscribe and hit the bell. Every week we cover the aircraft, the designers, and the decisions that changed aviation. Now back to a crash that almost killed the Stratoliner before it ever carried a single passenger. On March 18, 1939, less than 3 months after Eddie Allen's promising first flight, the prototype Stratoliner NX19901 broke apart over the forested foothills near Alder, Washington. All 10 people aboard were killed. The airplane had been carrying a crew of 5 and 5 passengers, representatives of the Dutch airline KLM, who were evaluating the 307 as a potential purchase for their Far East routes. Boeing was demonstrating the airplane's capabilities to a potential customer, which meant showing off the flight envelope. The details of the final minutes have been reconstructed from available evidence, witness accounts on the ground, and the wreckage analysis that followed. At some point during the demonstration, the aircraft entered a stall. From the stall, it fell into a flat spin, one of the most dangerous conditions any large, multi-engine airplane can encounter, and one of the hardest to recover from. In a flat spin, the aircraft rotates around a vertical axis while descending nearly straight down, with the nose roughly level rather than pointed toward the ground. Conventional recovery, push the nose down, unload the wings, build airspeed, becomes extraordinarily difficult because the aircraft's own rotation resists the pilot's inputs. The crew attempted to recover by breaking the spin and transitioning into a dive to regain flying speed. They succeeded in stopping the rotation. They got the airspeed back. What they could not survive was the pullout. The Air Safety Board's investigation concluded that the wings and horizontal stabilizers suffered structural failure during recovery from the dive. The forces generated as the crew pulled back on the controls. The aerodynamic loads of a heavy 4-engine airplane, transitioning from a near vertical dive back to level flight, exceeded what the structure was designed to absorb. The airplane did not crash because pressurization failed. It did not crash because the engines quit. It crashed because the aerodynamic loads in an emergency recovery exceeded the airframe's structural margins. 10 people died because the gap between controlled flight and structural failure was not wide enough. Boeing now faced a decision that could have ended the program. The world's first pressurized airliner had exactly one flight campaign behind it, a revolutionary concept to prove, paying customers waiting, and a prototype scattered across a hillside in Pierce County. TWA and Pan Am still wanted the airplane. The question was whether Boeing could make it safe enough to deserve their trust. They chose to redesign. The changes that followed were driven directly by the crash analysis and by a hard-eyed assessment of where the original design's margins had been too narrow. Boeing enlarged the vertical fin and rudder significantly. Not a subtle fairing adjustment, but a visible structural change that gave the airplane substantially more directional stability and yaw authority at all speeds. They revised the horizontal stabilizer geometry, increasing its area and adjusting its incidence to improve pitch stability. They added a dorsal fin extension forward of the vertical stabilizer to smooth airflow at high angles of attack. They strengthened structural members along the load paths that had failed during the prototype's final dive recovery, reinforcing the wing root fittings and the horizontal stabilizer attachment points to handle higher G-forces. The production Stratoliners that emerged from this redesign looked different from the lost prototype. Put a photograph of NX19901 next to a production SA307B and the change is immediately visible. The tail is bigger, the vertical fin taller, the overall profile of the empennage more authoritative. The production airplane carried wider margins and more robust recovery characteristics than the aircraft that had crashed. It was not a patch job. It was a genuine rethinking of the flight envelope's edges, driven by the knowledge of exactly what happened when those edges were exceeded. Boeing also used the redesign interval to refine the pressurization system for daily airline operations, hardening seals, improving the outflow valve's response characteristics, and simplifying some of the flight engineers' monitoring tasks. The airplane that entered airline service was more mature in every system than the prototype that had flown 10 months earlier. The first pressurized commercial flight in history came on July 4, 1940, when Pan Am's Stratoliner entered scheduled service. The cabin that passengers boarded that day was a revelation, not just in terms of pressurization, though that alone was unprecedented, but in the totality of the environment. Heated and air-conditioned in a sealed cabin where the temperature could be controlled regardless of the conditions outside. Furnished with reclining seats that adjusted to multiple positions for daytime comfort. Fitted with sleeping berths for overnight transcontinental routes, upper and lower, curtained for privacy, genuinely usable for actual sleep at altitude. A galley allowed hot meal service during flight, and separate men's and women's lavatories reflected the era's standard of decorum. The 307 offered an experience closer to a first-class Pullman sleeper car on the rails than to anything the air transport industry had previously managed. TWA's marketing made the most of the over-weather angle. Advertisements showed passengers gazing serenely through windows at cloud tops below. The implication clear: while other airlines' customers were being tossed around in weather, TWA's Stratoliner passengers floated above it all. For the first time, an airline could sell not just speed and schedule, but genuine comfort, and could back the promise with an airplane that actually delivered it. It is worth understanding what this means for the story that follows. Hughes did not take a crude, uncomfortable military transport and inject luxury into it. He took an airliner that was already the most comfortable in the world, an airplane designed from the ground up for passenger experience, and pushed it into an entirely different category. That distinction matters. Hughes' one-off SB307B, the variant with extra fuel tanks where paying passengers would normally sit, had made its own first flight on July 13, 1939, 4 months after the prototype disaster and months before Pan Am's service entry, Hughes had watched Boeing lose an airplane, bury 10 people, redesign the tail, recertify the type, and push through to commercial service. He had his machine, he had his fuel, he had the globe circling route laid out. Then history canceled the flight. World War II grounded the record attempt before it could begin. There would be no second circumnavigation. Hughes's purpose-built record ship sat idle on American soil while the world rearranged itself into something unrecognizable. During the war, the broader Stratoliner fleet went to work in a context nobody had envisioned when the type was designed. TWA's 5 aircraft were pressed into military service as C-75 transports. The Army stripped them of their luxury fittings. Out went the sleeping berths, the reclining seats, the galley equipment, the curtains and carpeting that had made the cabin feel like a Pullman car. More significantly, the military removed the pressurization systems entirely, eliminating weight and maintenance complexity that combat logistics did not need. The C-75s flew low and hard, back in the turbulence and weather that the 307 had been designed to fly above. An airplane built to cruise smoothly at 20,000 feet spent the war muscling through storms at 10,000 because the mission demanded cargo capacity and reliability, not cabin comfort. The irony was sharp, but the performance was real. The C-75s proved themselves on the Atlantic ferry routes, long, grueling overwater crossings where mechanical reliability mattered more than passenger amenity. They hauled priority freight. They carried VIPs under conditions that bore no resemblance to Pan Am's pre-war marketing brochures. The passenger manifests from those wartime crossings read like a directory of mid-century power. Winston Churchill flew the Atlantic in a Stratoliner. So did Madame Chiang Kai-shek. The airplane that had been built to pamper paying airline customers spent the war carrying the people who were deciding the fate of nations in stripped-down, unpressurized conditions that would have made Pan Am's sales team weep. The 307's wartime service proved that the basic airframe was tough, adaptable, and capable of sustained operations far outside its design envelope. It just proved it in the least glamorous way imaginable. Hughes' SB-307B sat out the war entirely. The record attempt was dead. The mission the airplane had been built for, the reason Hughes had ordered extra fuel tanks instead of sleeping berths, no longer existed, and the machine that had been designed for endurance and speed now needed a reason to keep flying. Hughes finally had the airplane and no mission to fly, so he gave it a new purpose and called in the most famous industrial designer in America to make it happen. After the war ended, Howard Hughes did something with the SB-307B that made it unique among all Stratoliners, and, arguably, unique among all aircraft of its generation. He hired Raymond Loewy to turn a 4-engine airliner into a private residence in the sky. Loewy was not an aircraft designer. He was the most celebrated industrial designer of the 20th century, the man responsible for the Studebaker Starliner's flowing lines, the Lucky Strike cigarette pack's iconic green and white redesign, the Pennsylvania Railroad's GG-1 locomotive, and later the interior of NASA's Skylab space station. Loewy's genius was making functional objects beautiful without sacrificing their function. Hughes wanted that genius pointed at the inside of his airplane. What Loewy did was strip the 33-seat airline configuration entirely. Every seat, every overhead bin, every partition and luggage rack designed for fare-paying passengers, and replace it with something that had no precedent in aviation. The strongest period sources document the conversion as including a fully equipped kitchen and bar, dedicated sleeping quarters, and a powder room. A separate authoritative account confirms the inclusion of a full bedroom, not a fold-down berth like the airline version offered, but an actual bedroom, private and enclosed. Taken together, the documented evidence describes an airplane that had crossed a line. It was no longer a transport. It was a residence, a pressurized, heated 4-engine apartment above the weather, finished to the standards of a man whose career had been built on making industrial objects feel elegant. Loewy understood something about the SB-307B that a less imaginative designer might have missed. The airplane systems, Its pressurization, its heating, its environmental controls already created a habitable space at altitude. What the airline version lacked was not livability, but privacy and luxury. Loewy's job was not to make the cabin function. Boeing had already done that. His job was to make it feel like a home owned by a man who could afford any home on Earth and chose this one. The broader embellishments that have attached themselves to the aircraft over the decades, a master bedroom, 2 full bathrooms, a sprawling living room with custom furniture and designer fabrics, fit the legend convincingly, but rest on thinner archival ground than the core facts. Period photographs of the interior are scarce. Detailed floor plans from the Loewy firm, if they survive, have not been widely published. What is established beyond reasonable doubt is this. When Loewy's work was complete, Hughes owned the most extravagant VIP piston aircraft in the world. Nothing else was in the same conversation. Private aviation in the late 1940s meant converted B-25 bombers with the bomb racks removed and a few leather chairs bolted to the floor where the bombardier used to sit. It meant surplus C-47s with the cargo doors welded shut, the bucket seats pulled out, and curtains hung over the windows to create something that squinted like luxury if you didn't look too hard. A wealthy businessman who wanted a private airplane in 1948 could buy a war surplus transport, have an upholstery shop in Burbank strip it and refurnish it, and end up with something that was essentially a cargo airplane wearing a suit. Hughes had a pressurized flying penthouse with a wet bar, a bedroom, and a view from 4 miles above the earth, designed not by a mechanic with a rivet gun, but by the man who had styled the Studebaker Starliner. The circular fuselage that Beale's team had chosen for purely structural reasons, because pressure demands a round cross-section, became an unexpected asset for Loewy. That tube was 11.5 feet across on the inside, lay a tape measure across the floor of a small Manhattan studio apartment, and you're looking at roughly the same width. But this studio had 4 Wright Cyclone engines on its wings, a pressurization system that kept the air breathable at altitude, and a range that could put Hughes anywhere on the continent without refueling. The shape that physics had demanded became the shape that luxury could fill. This is the moment where the 307's 2 stories converge. For Boeing, the Stratoliner was a proof of concept, the first demonstration that pressurized commercial aviation could work reliably, day after day, route after route. Every airliner that followed, from the Constellation to the 747 to whatever you last flew on, inherits something from the engineering that Boeing proved in the 307. For Hughes, none of that mattered. The 307 was raw material for something intensely personal. He took the most technically advanced airliner in the world and made it serve an audience of one. The kitchen existed because Hughes wanted to eat at altitude without landing. The sleeping quarters existed because he wanted to rest during long flights without sharing a berth with strangers. The bar existed because Hughes could afford to install a bar in an airplane. And no one, not Boeing, not the FAA's predecessors, not the laws of physics, could tell him not to. The powder room existed because Hughes, whatever his eccentricities, understood that a private airplane outfitted by Raymond Loewy demanded a certain level of finish. And here is the strangest turn in the whole story. Hughes barely used it. The most lavishly appointed piston aircraft ever built, the airplane that Raymond Loewy had personally converted, that sat inside the widest pressurized cabin of its era, that could fly above the weather in a comfort no other private aircraft could approach, spent much of its post-war life on the ground. Hughes had other obsessions consuming his time and attention. There was the H-4 Hercules, the Spruce Goose, absorbing millions of dollars and enormous political risk. There were the brutal corporate politics of TWA, where Hughes's controlling interest was dragging him into boardroom wars that would occupy years. And there was his own psychology, the obsessive-compulsive patterns that were tightening their grip year by year, making decisions harder, trust scarcer, and the world outside his controlled environments increasingly intolerable. The flying penthouse became something Hughes's life did not have room for, a beautiful, functional thing with no immediate purpose. He flew it occasionally. There are accounts of trips, of the bar being used, of the airplane doing what Loewy had designed it to do. But the grand vision, a private world above the weather, a flying home for the most famous aviator in America, never materialized into regular use. The airplane sat. In March 1949, Hughes sold the SB-307B to Glenn McCarthy, a Texas oil man and wildcatter whose appetite for spectacle matched Hughes's own. McCarthy had just opened the Shamrock Hotel in Houston, a launch party so extravagant, so chaotic, and so drenched in champagne that it made national news and inspired Edna Ferber's novel Giant. The airplane passed from one larger-than-life owner to another, and in doing so, it left behind the man who had made it singular. The strangest thing about Hughes' Stratoliner is not that he built it. It is that he barely flew it, and the airplane that was too early for its time outlived its purpose by decades. The Boeing 307 Stratoliner flew in commercial airline service for barely 5 years before the war swallowed it, and the type never returned to frontline scheduled operations afterward. The world that emerged from the war had newer, faster, more capable transports waiting. The Douglas DC-6, the Lockheed Constellation, Boeing's own Stratocruiser. The 307's production run of 10 airframes, its handful of years in pressurized service, and its wartime detour into unpressurized military work made it look, by the numbers, like a footnote. By its influence, it was a turning point. The pressurization engineering that Nate Price and Jim Cooper had developed, the supercharger bleed air, the automatic regulator, the sealed circular fuselage, the flight engineer systems panel, did not die when the Stratoliner left airline service. Boeing carried those lessons directly into the B-29 Superfortress. The B-29's pressurized crew compartments, which allowed bomber crews to operate at 30,000 feet without oxygen masks or heated flight suits, descended in a straight engineering line from the work Beale's team had done for a commercial airliner. The problems were the same: seal a metal tube, pump air in, regulate the pressure, keep humans functional at altitudes that would otherwise kill them. The solutions were evolved versions of what had already been proven over Pan Am's routes and TWA's transcontinental schedules. The airplane that Boeing designed to make airline passengers comfortable ended up making strategic bombing possible at altitudes where anti-aircraft fire and interceptors were less effective. From the B-29, the technology branched outward. Boeing's post-war Stratocruiser used pressurization. The DC-6 and Constellation used it. Every subsequent airliner used it. The sealed pressurized fuselage became so universal that within 2 decades of the 307's first flight, passengers had forgotten it was ever remarkable. That forgetting was the ultimate vindication of Eddie Allen's first flight assessment. The whole point was that you shouldn't know you're up there. Of the 10 Stratoliners built, one survives intact. Pan Am's Clipper Flying Cloud sits in the collection of the Smithsonian's National Air and Space Museum, restored and preserved. It is, by any reasonable measure, one of the most important airliners in history. The airplane that proved pressurized commercial flight was practical. Most people walk past it without knowing what they're looking at. Hughes's airplane took a different path entirely. The SB-307B's fuselage, the shell that once held Loewy's kitchen, the sleeping quarters, the bar, and the powder room, passed through several owners after McCarthy and eventually found its way to Fort Lauderdale, Florida. There, in one of aviation history's most improbable second acts, it was converted into a houseboat. The first pressurized airliner fuselage in history spent its later years floating on the water near Biscayne Bay, known by the name Cosmic Muffin. The circular cross-section that Beale's team had chosen, because pressure demands a round shape, turned out to make a surprisingly seaworthy hull. A pressurized Penthouse that once cruised at 20,000 feet, reborn as a floating home on the intracoastal waterway. There is no cleaner image of what happens to a machine that arrives before its time. The world catches up, passes it, and the artifact gets repurposed into something its builders could never have imagined. The 307 matters because of what it proved. You could seal a fuselage, pressurize it with engine bleed air, regulate the environment automatically, and carry people above the weather in safety and comfort. That proof changed commercial aviation permanently. And for a few years, in the late 1940s, there existed one airplane that was simultaneously a triumph of engineering, a monument to private excess, and a pressurized living room in the sky, powered by 4 radial engines, furnished by Raymond Loewy, and owned by a man who wanted to live above the weather alone. The airplane did not change the world in the way Boeing planned. It changed it in quieter ways that lasted longer. Thank you for watching. If you found this one valuable, a like and a subscribe go a long way. We cover the aircraft and the stories behind them that most channels don't. And until next time, fly above the weather.